Welcome to this explainer. Today, we're going to completely redefine how you look at the heavy, static world of industrial engineering. You know, when you drive past a massive oil refinery, a chemical plant, or a power station, those thousands of steel pipes look like the most rigid, immovable objects on Earth, right? They just sit there. Well, actually, no. Today, we're peeling back the layers to see what's really happening on a molecular level. And trust me, it is far more violent and dynamic than you might think. So let's dive right into this totally counterintuitive question. Because naturally, most of us assume a broken pipe means a massive, catastrophic fluid spill. We picture a water main bursting out in the street or some dramatic movie scene with high pressure steam spraying absolutely everywhere. We're pretty conditioned to equate failure with a visible breach. But the terrifying reality, a pipe can completely die from invisible internal damage long before a single drop of liquid ever escapes. So the answer is a resounding yes. A pipe can fail by buckling under its own restrained pressure, crippling in on itself, or succumbing to something we call low cycle fatigue. We're going to explore exactly how these invisible forces wage an all-out war on solid steel, and how engineers somehow manage to keep our infrastructure intact. All right, Section 1. Defining a pipe's failure. To really understand how a pipe fails without springing a leak, we've got to redefine what the word failure actually means when we're talking about solid steel. It's not just about a hole or a rupture. It's about the material fundamentally losing its structural integrity. And to grasp that, we have to look at the yield point. This is the absolute maximum threshold where a material can bend and still completely return to its original shape. Think of it like a plastic ruler. You bend it a little bit, let go, and it snaps right back. That's elastic behavior. But if you push past that threshold, you cause permanent, irreversible deformation in the metal. It's yielded, it's permanently bent out of shape. And in piping stress analysis, managing that yield point is quite literally a matter of life and death for the facility. Moving on to Section 2, the 3 invisible attackers. Once a pipe is actually built and installed, there's this whole lineup of invisible attackers constantly trying to push the steel past that critical yield point we just talked about. First up, primary stresses. These come from sustained loads. Think of the massive dead weight of the pipe itself, the heavy insulation, and that constant internal fluid pressure pushing outward. If these get too high, the pipe just continuously yields until it bursts. Then we have secondary stresses. These come from expansion loads, usually thermal growth, which causes distortion and buckling. And finally, peak stresses. These come from occasional or cyclic loads, zeroing in on weak points and causing long-term fatigue. Which brings us to Section 3, the threat of thermal expansion. What's absolutely fascinating here is that if a pipe is locked down tight, say it's anchored rigidly between two giant pieces of equipment, the internal strain from hot fluid will literally cause it to buckle and pop right out of the ground. Thermal expansion is just this monstrous, unstoppable force. When hot fluid flows through, the metal naturally heats up and tries to expand. If it's completely restrained and has literally nowhere to grow, the internal stress skyrockets and that pipe destroys itself from the inside out. So, how do engineers combat this? They use a brilliant mathematical trick called the shakedown effect. The golden rule here is that if the secondary stress is kept below twice the yield stress, engineers call that 2SY, the pipe safely adjusts and bends without breaking. This principle basically allows the pipe to yield just a tiny bit initially, so it takes on a localized plastic deformation, but then it settles right into a safe, elastic range for all its future operations. I love this analogy because it perfectly illustrates the physics. Think of a stiff pair of leather shoes. Just like breaking in new shoes, a pipe yields slightly the very first time it heats up, forming a permanent, comfortable crease. But after that initial distortion, it's broken in. It comfortably bends and flexes within a safe elastic range during all the future heating and cooling cycles. It literally shakes down to a comfortable fit, letting the plant operate safely for decades. But what happens if it doesn't shake down? Well, if the stress goes too high, the pipe yields in compression every single time it cools down. As we can see, going beyond the yield here, every single temperature change causes brand new, invisible plastic damage. It never settles into that safe, elastic zone. And that continuous, hidden internal damage is exactly how a pipe structurally fails without ever spilling a single drop. It is a direct, silent path to structural death. Now for Section 4, the paperclip effect. So, if a pipe constantly alternates between extremely hot and extremely cold states, it experiences what engineers call a reversal of moments. This fatigues the metal exactly like snapping a paperclip back and forth. You know the drill. You bend a metal paperclip once, it holds its shape perfectly fine. But bend it to the left, then to the right, reversing that moment over and over, the metal quickly fatigues and just snaps in half. That is exactly what peak stress does to heavy industrial pipes, silently, over thousands of thermal cycles, causing it to completely fail without a single warning leak. To get ahead of this, engineers actually use a formula called the cumulative usage factor, or U equation, to meticulously track that exact paperclip effect. It basically sums up the fractional damage from all those various stress cycles over the entire lifespan of the pipe. You definitely don't need to memorize the math here. The vital takeaway is simply this. When U equals exactly 1, the pipe's fatigue life is 100% consumed. It's a dead pipe walking, structurally failed on the inside before a visible breach ever has the chance to occur. All right, let's wrap this up with Section 5, how engineers prevent catastrophe. With primary, secondary, and peak stresses constantly trying to tear everything apart, how do we actually prevent it? Well, engineers know they can't lock a system down completely. If you treat a rigid pipe under thermal expansion like pushing both ends of dry spaghetti together, it snaps instantly. Instead, they build in flexibility to make the pipes act way more like a bendy straw. Take an expansion joint, for example. It's corrugated, right? So it safely compresses and absorbs that physical growth without transferring those dangerous destructive loads to the rest of the system. To stop these invisible enemies before a single piece of steel is ever even cut, engineers follow a super rigorous process. First up, they simulate the physics using advanced software, like Caesar 2, plugging in all the environmental conditions, temperatures, pressures, and weights. Second, they apply stress intensification factors, or SIFs, to mathematically multiply the danger at known weak joints, stuff like sharp elbows or T-branches. And finally, they take all that incredible simulation data to design and deploy physical armor using flexible hardware routing. And that physical armor includes some seriously massive components. We're talking enormous U-shaped expansion loops that naturally flex to absorb thermal growth. They install those corrugated expansion joints we just mentioned. They also use specialized spring hangers that literally let heavy vertical pipes move up and down as they heat up while still continuously supporting thousands of pounds of weight. Plus, they use guides that allow the pipe to slide horizontally without twisting. It is truly amazing how all this hardware works perfectly together to let the pipe breathe, grow, and move without tearing itself to shreds. So, as we close out this explainer, I want to leave you with a thought that really changes how we view the industrial world. The next time you look at a sprawling industrial plant, ask yourself, what terrifying, invisible forces are those seemingly static metal tubes battling at that exact moment? Because they aren't just sitting there passively. They are actively surviving massive pressure, extreme thermal expansion, and continuous fatigue, all thanks to some mind-blowing physics and meticulous engineering. I really hope this gave you a brand new appreciation for the hidden mechanics keeping our modern world running.